Alright, so in this video we're going to take a look at byte ordering or Endianness. So the phrases here are byte ordering and Endianness. You might be wondering where this comes from, this Endianness thing, and this actually comes from a Jonathan Swift novel, Gulliver's Travels, where Gulliver gets transported or whatever to an island full of this interesting civilization and so on. Anyway, in this story and so on, there are people who break an egg or peel an egg from one side or the other and so on. And there is a degree that you should always peel from the little end, the smallest end of the egg or whatever, the thinnest, and so on. So anyway, Endianness refers to effectively the order of bytes. So that's why we call it byte ordering as well. And what that actually means is where is the most significant information in a multi-byte value, right? So we had this value that we looked at last time, 18 for the 2204 and so on. And we know here that we can section this into different values, different sections like this. We could actually make this even more obvious and say x bytes is actually transmute, and then we're going to make 4 bytes out of this, and I'm going to show you why this doesn't work by default, and then we're going to correct this error. Here we're going to say, let's print this. So we have 0 to x like this. I think this should work. And then we have x bytes like this. And here we can't transmute x because it's 8 bytes. And that's of course because this is an integer by default, because we haven't said anything, right? So we're going to put a type here, U32, which is of course 32 bits, and that's 4 bytes, right? Now we can actually print this. Let me clear this and then open. There you go. Now we can see, okay, this is the actual ordering of the bytes. And there's something interesting going on here, right? So we have this number. The number itself is not super interesting. We have the hex representation of this value, which is just a series of bytes that are regarded, right, as one number and so on. And we can see here that the actual data that this transmutes into does not necessarily follow that order. In fact, it is completely the opposite, right? This is because on this architecture that I'm running on, x64, so x86 64, also known as AMD 64 or whatever, and x86 by just from the beginning is a little-endian architecture, right? So you might find other architectures that are different. The M1 architecture is actually little-endian, if you're wondering about this. ARM supports both, in fact. So what that actually means is something could be making a decision for you, but it's not the actual processor architecture that's making the decision in this case. x86 is always little-endian, right? That is, when it reads memory, stores memory, etc., it will store it little end first. So we will get effectively the smallest end, the end that accounts less for the actual max value or the actual value of the thing that we're storing, right? That will come first. So we're effectively reading this byte, this byte, this byte, and then this byte, right? Of course, the notation here, the way I'm writing this is still, I'm writing it in order, right? Let's say the order that makes sense for the actual values, right? And so on. But it's stored like this here, right? And so Odin has a few tools for us to talk about these things. So we can say, for example, XLE here for little-endian, U32LE, right? Let's say that this is 0x18, etc. Let Copilot do this. So XLE bytes would be this, right? Let's say also XBE, U32BE, right? 0x18, etc. XBE bytes, etc. Here we're gonna just go with this, and now we're gonna print these as well. So here we have little-endian. Here we have big-endian, right? Let's print those. We can actually see this in action. And so here, just by sort of specifying in a certain way, right, we have now been able to, well, first of all, be clearer about what's going on, right? And also, we can see here the difference, right? This stores the what's known as the most significant byte first, right? So if we have 4 bytes, for example, we have let's say 0, 0, 1, 1, 2, 2, and 3, 3, right? This is the MSB here, right? And this is the LSB. Let's move that there. So most significant byte, least significant byte, right? For some ordering, right? So big-endian is this, right? Little-endian would be this, right? So that's the difference. And you might wonder, you know, hang on, like why do I have to care about this, right? Well, the truth is different architectures have used different orderings. There's also additional complication. Historically speaking, of course, we have not always run the same kinds of computers, right? As I said, previous architectures could have, basically, they could be big-endian, right? And so on. On top of that, we have something called network byte ordering. So if we go here, we can see that in networking, there's what's called the network byte order or network order. That is big-endian. So regardless of the fact that we primarily nowadays use little-endian computers, like this is the vast majority, right? We still have to account for this, right? And the way historically that this has been handled is that you have these conversion functions. So if I go here, we can see, maybe it's byte order actually. Yeah, okay, so here we can actually see that we have utility functions for dealing with some of these things, right? On top of that, we have, let's see, okay, that's weird. So here we can see H2NL and so on, N2HS, etc. These are conversion functions that a system can implement, right? And they will be implemented in such a way where we can now generalize. We can basically say, oh, this is from my host computer to network order. So that's what these things stand for here. Host to network long, right? Host to network short, right? So the S here and the L are sizes for the actual value. H and N are where am I and what am I trying to send to. Host means the computer I am on. N means network, meaning we're converting to network byte order, no matter what that might be. Let's say I'm running on a processor that already uses big-endian, right? That architecture I'm using is already big-endian. This does nothing in that case, right? But it's implemented for that system, right? Host to network in that case will be a no-op. It will do nothing. It will just pass the bytes through, right? And of course, I would say historically, this has become kind of less and less of an issue. It's not an issue that we need to care about less in terms of it existing, But it is an issue less that we are not necessarily always going to default to network byte order. If you are writing servers and you know that these are going to be deployed on little-endian architectures and so on, this could be work that you do not need to do. You could also always mandate little-endian. And then any version of that protocol that will run on a big-endian computer simply needs to adapt to little-endian. It is not necessarily harder than that either, right? But yeah, these are things that we need to think about, because of course data is stored and then it's read. It could be stored on one computer, read on another. Things change over time and so on. So we do need to care about the idea of byte ordering, right? And here is how we can relate to this, like this, right? And this comes up, right? So as an example of this, if we go to, for example, the LZ4 frame format here, right? LZ4 is a compression algorithm. And the values here, we will see, and this is generally speaking going to be the case, right? When you have a file format, you are going to be specifying, hey, what is this order, right? And so, for example, here, this magic number that we can look for, right? When we look for this in files, it's important to understand the value here is specified essentially big-endian, right? So we have to mentally then say, hey, what value am I looking for? I'm looking for the bytes 04, 22, 4D, 18, because it has specified little-endian, right? The notation here still says this is big-endian, right? And just to kind of illustrate this, right? If I do go here, let's see here, we have this, I can say dhex, let's say bags. If I go to search here now, right? So for example, let's say I naively said, okay, I'm searching for 18 4D 2204, right? 18 4D 2204, right? And now I'm going to search forwards and go. Let's see, open forwards and go. Nothing, right? But if I'm aware, oh, hang on, this is in little-endian, right? We can see 04, 22, 4D, 18, right? So now I'm going to search again. We're going to say the search string is actually 04, 22, 4D, let's see, 18, right? Like this. We're going to say we're searching forwards and we're going. And now we can see we found this, right? At the top of the screen, you'll see 04, 22, 4D, 18. And this is how we identify when a frame in LC4 starts, right? So if we were to search for this in files, we can in fact see here is where this starts, right? So we do have to understand what is the difference here between this notation here, right? And the actual thing that I'm going to be looking for, right? And so in practice, what this actually looks like, if we quit this here briefly, we are not going to save our changes, is when we run a program like this LC frames here on bags, and we want to find frames and sort of output their sizes or whatever, right? When we actually have this program, if I go LC frames here, we can see in practice that the value that we're looking for is in fact this value. The magic bytes, as they're called, right? The magic value here is in fact this byte pattern. And when we actually look for that one, that's how we will find it, right? So we do have to be aware of what is this, byte ordering thing, right? Likewise, when we are producing materials, for example, or we're sharing knowledge about something, we also have to understand the difference here, right? We have to specify these things. And of course, you saw in Odin, we do have these types that makes things very specific. If something is in fact stored big-endian, we can make a type to represent this. And when it's read from these bytes, we will then actually get it in the correct shape. Like we will get the correct value. Right. So this was a fairly short video on byte ordering and so on, and kind of why it matters, when it matters, and so on. You have to be aware of this, right? Because you are going to be looking at data. So we saw, for example, when I ran dhex here, right? We are looking at raw data here, right? We're looking at just the bytes in a file. And of course, I'm not saying you should use dhex necessarily. You can use whatever hex editor or hex viewer that you might find, or, you know, you can have your own process here, right? I'm saying that this actually matters, right? We do need to care about these things, generally speaking, right? You will be implementing file formats at some point. You will be sending things over the network at some point. Something will be deserialized at the end of that, at the other end of that. And that will have to understand, if you're serializing actually binary data, it has to understand the structure of that data, right? We have to specify those things. We have to be clear on those things, right? Because otherwise we will run into situations where we haven't specified stuff and now we're just having assumptions everywhere that don't hold at some point, right? So that's byte ordering, and it's important to understand that this does not apply when we have just a byte. It does not change the order in which a byte is actually structured, right? That would be called bit ordering, and it is a thing, though I have never, ever seen this come up. But that's probably because I haven't done the things where bit ordering actually matter, like communication systems, meaning the absolute lowest level of a communication system, right? I'm sure people who deal with network cards and so on and the absolute low level stuff there, they probably care about this a lot, right? So you can have the same concept there, right? But when it comes to reading, writing bytes and so on, we care about byte ordering, right? So yeah, I hope that this video was informative. Next video, we're going to be talking about deconstructing bits and bytes, basically looking at values that are, looking at extracting and modifying values that are smaller than a byte. So we're going to be doing what's known as bitwise operations on those to deal with that. And we will also be looking a little bit more at the LZ4 example and so on. That's it for this video. Like I said, I hope it was informative. If you like the content and you like what I'm doing here, please like and subscribe. Share your feedback if you have it. Share just nice words if you have those as well. I'm happy to hear them. That's it for this one. Have a nice day and ciao.